going to do section 11.7. This is a great section to practice your skills now that you've learned some of the tests. You do have to practice in the individual sections first, because you need to know what test you're supposed to use for a while, and then once you can do that, this is a great place to test yourself. Okay, so this the first one here, number 1. When I look at it, I kind of ignore the n and the 3 to the n, and I just think, what does it look like? What is a series that I know about that looks like that? That's another way to look at it. So I think immediately of 1 over n, or 1 over 3 to the n, and which is the one that's most dominant here? Is it the 3 to the n or the n? And my experience tells me the 3 to the n is much more powerful than the n, so I'm thinking this is really similar to 1 over 3 to the n. Okay, and that's also written as 1/3 to the n, which is a geometric series. So that converges. Okay, so now I'm thinking that this converges. Now, can I compare them? Sure. Let's do n plus 3 to the n. That's definitely greater than 3 to the n. So 1 over n plus 3 to the n is less than 1 over 3 to the n. Okay, so the sum of n plus 3 to the n is less than the sum of 1 over 3 to the n, which converges. Okay, so therefore, the one we were interested in converges. You could also do limit comparison. If you're inclined with 1 over 3 to the n. We'll use L'Hopital's rule for that. Okay, number 2. When I see this, I see these powers of n, and so as a person who's had to make these myself for exams, I can tell you that this is just a trick. This is to disguise that this is designed for the root test. Because if I wanted you to know that this was written for the root test, then I would have helped you out as much as possible, and I would have written it like this, which is exactly the same thing. So what you need to do is to practice that. When you see that n in both places, rewrite it like this. And now this is a perfect setup for the root test. Okay, so let's do the limit as n goes to infinity of the nth root of that thing. Of course, the nth root, that's the same as the nth root there is really a 1 over n power, and so these just cancel. Okay, so now those are gone, and I can take this limit, which is 0, and the root test says that if that limit is less than 1, then it absolutely converges. The issue of absolute convergence wasn't really even necessary here. There's no, everything's positive anyway. So, let's move on. Incidentally, the ratio test wouldn't be as good here. It would work for the exponents, but it would start to get a little messy in here because you'd end up with an n plus 1 to the 2, n plus 1, to 2 times n plus 1. Anyway, so root test is perfect for it. But you had to see this. Okay, number 3. Alright, this here, immediately, if you look at this, the limit is 1, and so this fails by, or it passes the divergence test if you look at it that way. So this is divergent since the limit of n goes to infinity of n over n plus 2 equals 1. You'll probably have something like that on your test. I've said that many times. You got to just take the limit when you first see it. If you look back up here at this one, okay, I agree that taking the limit when you first see it is a little bit uncomfortable. So when you see that, it probably does go to 0. And this, when you write it this way, you can see that it does. This goes to 0 on the inside. But anyway, if it's too hard to do it, then don't. But if you can glance at it and see that the limit goes to 1 immediately, then you can say that it's divergent and you can move on. Number 4, this is an alternating series. I see a couple of things immediately. I see that I could integrate this. I see that this is very similar to 1 over n, and I see that it's an alternating series. So I have a couple of choices here. I can, let's use the alternating series test, because that just requires that I show that it's decreasing and the limit is 0. And then we'll check to see if it's absolutely convergent or not. It doesn't say to do that in the directions, but we'll do it anyway as an exercise. Okay, so the alternating series test is I need to show it decreasing. Okay, that's where it says a n plus 1 is less than a n. That means the next one is less than the previous one. So another way of saying decreasing. And then I need the limit of a n equals 0. Okay, so you can see that the limit is equal to 0. The limit n over n squared plus 2. The power on the bottom is bigger, so this is equal to 0, so number 2 checks. Let's check the decreasing. The easiest way to just do this, I mean, if you're not comfortable showing that these terms are less than each other by placing n plus 1 in there, and you shouldn't be if you're new to this, it's probably normal to not be comfortable with that, then you just go for the derivative. And you know, just take the derivative as normal. Pretend it's f of x over x squared plus 2, and then take the derivative. We have to use the quotient rule, so if we're going to do that, this times 1 minus x times 2x over x squared plus 2. I know from experience, having done these, they don't put them in the book and have you do this unless the derivative is sort of easily shown to be negative. So let's see if that's the case here. I have this squared on the bottom. On the top up here I have 2 minus x squared. This is 2x squared and this is positive x squared, so we put them together we get negative x squared. And lo and behold, look how negative that is. X is things bigger than 1. So, you know, after 1, once it gets to 2, then it's 2 minus 4 and 2 minus 9, things like that. So, definitely negative after a while. The first term it's not. But, yeah, so this is, you know, for x greater than 2, it's less than 0, so we have what we want. We have the decreasing. So this is a convergent series. Okay, now what about absolute convergence? So to check absolute convergence, all I do is remove the negative here, and I check. Let's check the series, the absolute value of it, which cancels out the negative, just for practice. And this is a very good example of something that you would get on your final exam right here. Okay, so there's a couple of ways to go here. You could integrate this. And you would show that it's divergent. But the easiest way is to realize that this is really similar to 1 over n. Okay, and that diverges. Okay, so let's divide that up. So let's do limit comparison. We'll do the limit, n goes to infinity, n over n squared plus 2. Now I'm going to divide by 1 over n. See if you agree that that's the same as multiplying by n. So I'm going to divide by 1 over n, but what I could do is I could just multiply by n. That's the same thing. Alright, so I'll still write all that down, but if you're getting ready for an exam, you want to look for those kinds of things, because this is confusing to look at when you're in an exam. So if you can avoid it, just say, well, that's the same as multiplying by n. So that's n squared over n squared plus 2. You're taking the limit here, and that's equal to 1. Okay, so we have a constant less not equal to 0. And so both either converge or both diverge, but since 1 over n was a divergent series that we used, that means this one diverges. So what we finally say is that the original series is conditionally convergent. So there's a lot to that problem. Take that problem and repeat it, and take a clean piece of paper and reproduce that, all those little details, and that'd be a good download. Actually, all of these are great for that. Alright, see if I can squeeze another one in here. Number 5. Do number 6. I don't have enough time for that. Okay. So again, this one here, maybe having done the one previous to this, you might realize how to do this one immediately. Maybe I'll do this one by the integral test. Here, you can integrate this if I just look at the integral from 1 to infinity. Here, if this is convergent, then that'll be convergent, and if this is divergent, then this will be divergent. Okay, so we'll let u equal 2x plus 1, du equals 2 dx, dx equals 1/2 du. This is equal to the limit as t goes to infinity, 1 to t of 1 over 2x plus 1 dx, which is the limit as t goes to infinity. And then replace all that, I get 1 over u, 1/2. Trying to fit all that in there. U is equal to 2x plus 1. So what we finally have is a limit as t goes to infinity, 1/2 ln 2t plus 1 minus ln of 3. Right, and then as t goes to infinity, this goes to infinity. So this is divergent, which means the original series is divergent too.